Welcome to our program Effective and Efficient Electronics for Excellence. In today's presentation, that is our lecture number 49, just I would like to explain you finding the transfer function of a few electrical networks or electrical circuits, the basic circuits actually. It is like okay, like your RC network. Okay, let us see. Okay, so I will explain you an example based on finding the transfer function. Let us consider one simple example that RC network basically. This is very simple network to consider. This is very simple network which is to be considered as to understand the concept of transfer function. This is, let us say, R, this is C, this is your Vi input and this is your V naught output. Okay, this is the resistive element, this is the capacitor element. So for this, the question is find out what is V naught of S by Vi of S. What is this? This is what your transfer function actually. It is the ratio of output by to the input. V naught S by Vi of S. Where, okay, first of all, we need to find out what is Vi of S and then what is V naught of S. Then take the ratio, then you will get basically. In general, for your kind information, if you see here the combination of RC, it is a RC network basically. This is resistor and then capacitor. Whenever the resistor is connected with capacitor in this fashion, it acts as a low pass filter. It is called a low pass filter. Basically, this is in general the standard form of any low pass filter. The resistance is okay in this connection like capacitance. Then it is called a low pass filter, and also it acts as an integrator. It acts as an integrator. Integrator means your output. So means your output V naught is equal to integral of your input actually. Okay, so output is nothing but integral of input, means it is a integrator, an integrator circuit. Clear? That is what the basic thing basically in electronic circuits. Wherever we need the application of using integrator, there we will use basically this RC circuit. Clear? Now let us see that. So if it is for this particular circuit, so let us say V, so this is V suffix R is the voltage across the resistor, and again here it is V suffix C is the voltage across this capacitor. Let us say plus and then minus. This is again here plus and then minus. This is plus and then minus. For this circuit, let us say VR is the voltage across resistor and VC is the voltage across capacitor. Then according to your KVL, if you apply the KVL here, as per that, VI input voltage is equal to your VR plus VC. Clear? It is the sum of resistor voltage plus capacitor voltage. What is the, let us assume that the current I is flowing through this loop. If you consider this as a loop, then your I is called a loop current. Then what is VR? Voltage across capacitor, that is R into I. R into I plus, or otherwise you can say you can write the Laplace transformation form. Then you can write I as some I of S definitely. Means then you write R into I of S, because R is a constant always. I of S is a current input. So current input always depends on time. Therefore, that should be converted into Laplace transformation domain. It becomes I of S. R into I of S. Clear? plus what is VC? VC is nothing but voltage across capacitor. That is nothing but 1 by S into C. 1 by S into C integral of I dt. Integral of I dt, or 1 by C, actually 1 by C integral of I dt. Integral of, I will write this, sorry, 1 by C integral of I dt actually. This is what the voltage across capacitor. 1 by S is nothing but the Laplace transformation, but this is actual domain, or even you can say some I of t, because we are taking the time domain. I of t you can write, because this is V I of t, basically V I of t is equal to R into I of t plus 1 by C into I of dt. This is the expression, call as 1. Now apply the Laplace transformation. By applying Laplace transformation to the equation number 1, then it will becomes, it is V I of S, V I of S, because time domain converts into S domain. V I of S is equal to, now you write I of S here. This is R into I of S plus 1 by, so 1 integration means definitely it should come 1 S in denominator. 1 by S into C, already it is there. 1 integration indicates 1 S in denominator. Then it becomes I of S. I becomes I of S. Clear? And then from these two you can write, you can take I of S as common. If you take I of S as common, this implies your V I of S is equal to, if you write I of S as common there, then you will have R plus 1 by SC. Clear? R by 1 plus SC. This you can call it as your equation number 2, for example, right? You call this as equation number 2. This is what from your loop, from this first loop. Now V0 can also be written as, the output V0 can be written as V0 is equal to, V0 of t is equal to, V0 is nothing but voltage across capacitor. That is nothing but again 1 by C integral of I into dt. Same current. 1 by C, same. This, okay, V0 is nothing but voltage across capacitor, nothing but your VC actually. V0 t is equal to VC, that is nothing but this one. Okay, V0 is equal to VC, like this. Here VC is there, no? This particular V0 is equal to VC. VC is nothing but this much. So for this, now you apply the Laplace transformation, then it becomes V0 of S is equal to 1 by 1 integration means 1 S will come here. See, anyhow it is there, it is I of S. Clear? So from this expression you write I of S. I of S is equal to, from this I of S is equal to, what is that? Take cross multiplication, S into C into V0 of S. Clear? Now you can write this as, let us say, you can call this as equation number 3, because we are writing expression for V0. And finally from this you apply the Laplace transformation, you will get this expression. And from this you are taking the value I of S. I of S is equal to this much, and you give some 4 here. Now substitute equation 4 into equation 2. Substitute equation 4 into equation 2. Then how it will come? I will explain you here. If by substituting equation 4 into equation 2, then it becomes V I of S is equal to what is I of S? This one. Whatever I of S equal to this much. This is what your I of S, no? Substitute this I of S value there. Then S into C into V0 of S. Clear? This is what your I of S. In bracket, the another parameter is there, R plus 1 by SC. Clear? This is what. From this, what is my objective is to find out V0 of S by V I of S. I want to bring the relation between ratio of V0 of S by V I of S. Okay, V0 of S, you okay, you bring Vi of s to this side, then obviously you bring the entire to the second, I mean right side, then definitely how it should come, the entire should go into 1 by basically, okay, it comes, or otherwise for your this thing you can write as like this also. You can simplify here this Vi of s, let it be, next we will write in the second step, and V naught of s, so your V naught of s will be like this. You take SC into inside, means it becomes then RSC plus SC by SC. Clear? These two will be cancelled out, one will be here. Therefore, V naught of S is equal to 1. This is SC by SC, nothing but 1. 1 plus RSC I can write. Or S, S or C. You can write like this also. You can take S into RC. This is what your Vi of S. Therefore, now it is easy, no? Now bring the ratio V naught of S by Vi of S. V naught of S by Vi of S. Nothing but 1 by 1 plus S into RC. This is what your transfer function basically. This is what your transfer function basically. Clear? But and little bit further to this expression, you can write like this also. V naught of S by Vi of S is equal to, it is 1 by 1 plus S into tau also. Remember that. This ratio is called as your transfer function basically. This is what your transfer function. Tau, where tau is equal to R into C. This is called as time constant. Tau is called as time constant. Okay, time constant. Time constant of RC circuit. So this is what your 1 by 1 plus S tau. This okay, this is what the expression, I mean the ratio of this expression. So this is simple RC circuit, and it is of low pass filter, you can say. Clear? So we will finish off this here, and then we will continue with another example in the next presentation. Okay, see you.